linear, quadratic, and rational inequalities. Let's consider the following example. Solve the inequality 3x plus 3 is less than 2x minus 1. You might recall from elementary algebra that to solve an inequality, you pretty much approach it like you would approach an equation, at least in this case. So we have the following, and the general strategy is that we would like to get all of the variables on one side of the inequality and the numbers on the other side. So here I can subtract 2x from both sides. So this is a property of inequalities. 3x minus 2x is x, and on the other side you have negative 1, and the inequality stays the same. Now to get x completely by itself, we'll subtract 3 from both sides, and this gives us x is less than negative 4. And this is our solution. And so in order for this inequality to be true, x can be any number less than negative 4. Now let's talk about how we write the solution. Of course, one way to write the solution would be to just express it as you see here. But there is another way to do it called set notation. And so we are going to describe the set of numbers, x, such that x must be less than negative 4. So we're saying the solution is all the numbers x that satisfy the fact that x must be less than negative 4. Now, this is actually not the notation that I prefer. I prefer interval notation. And to understand interval notation, it is important to first draw a graph of what this solution would look like. So x is going to be all the numbers less than negative 4. So if we have negative 4 here on the number line, we want all the numbers that are less than negative 4, and that would be all the numbers to the left of negative 4. And it's not equal to, and so what we do here is we put a parentheses to indicate that we are not including negative 4. And then you need to remember that when we go forever to the left, this is basically negative infinity. And so in interval notation, the way you describe this is all the numbers coming from negative infinity going up to the number negative 4. And so we would write that like so. So let's talk a little bit more about interval notation. So on the left here, you see the inequality notation for various intervals. And then you see the corresponding interval notation. So here, when we say x is a number in between negative 3 and positive 2, on a number line, you can see it as this. And then, as we just mentioned, since there's no equal to signs here on these inequalities, we have parentheses. And so the interval notation would be all the numbers from negative 3 up to positive 2. Now, there is another way to indicate that you are not including the endpoints, and you can do that by using the open circle here, whereas a closed circle, like you see here, would indicate that it is included. Okay, so this is an alternative way of doing it, but for this class, let's just go ahead and not worry about that. We're always going to use this method. So what you'll see is all these intervals are basically the same. We're talking about all the numbers x in between 2 and negative 3. The only difference is in some of the intervals, the endpoints are included, and in some, they are not. So for example, this one here says all the x values in between 2 and negative 3. Negative 3 is included because it says equals, but 2 is not. So you see a bracket here, which represents inclusion, and a parentheses here, which represents not including. And the corresponding interval notation is here. So let's go ahead and solve the next inequality, and we'll put our answer in interval notation. So we have negative 2y minus 3 is less than or equal to negative 7. First, I'll add 3 to both sides. This gives us negative 2y is less than or equal to negative 4. And now to solve for y, we have to divide both sides by negative 2. Anytime you multiply or divide by a negative, the inequality that you see here is going to reverse in the next step. So on the left-hand side, we have y. On the right-hand side, we have 2. But now this is going to flip to be greater than or equal to. And so this is our solution. Now on a number line, we are talking about all the numbers equal to 2 and greater than 2. So notice that it's going forever to the right here, which means it's going to infinity. So in interval notation, we start at 2 and we go to infinity. So interval notation, when you do this here, you always go from left to right. So in our next example, it's the same as solving an equation. First, we'll want to multiply out the parentheses, which gives us 6x minus 12 minus 7x less than or equal to negative 3x. Next, we'll combine like terms. 6x take away 7x is negative x, and then we still have minus 12 less than or equal to negative 3x. Now from here, you can actually proceed a couple of different ways. Most of the time in this situation, I would probably add x to both sides because that would get all of our x terms on the right-hand side. But when you're solving inequalities, it's actually better if you always get your variable on the left-hand side, okay? So what I'm going to do instead of adding x is I'm actually going to add 3x to both sides. This is going to give us negative x plus 3x is 2x minus 12 less than or equal to 0. And now to get the x by itself, I'll have to add 12 to both sides. And that gives us 2x is less than or equal to 12. And now I'm going to divide by 2. And since we're dividing by positive 2, the inequality here does not reverse. So we end up with x is less than or equal to 6. And in interval notation, first let's sketch a graph. So here is the number 6. We want all the x's that are less than 6 or equal to 6. So again, since we're going forever to the left here, that's negative infinity. And so in interval notation, we are starting at negative infinity and going up to positive 6, including positive 6. In our next example, we are simply graphing the set of numbers x such that x is less than or equal to negative 2 or x is greater than 3. So the graph of these numbers is fairly straightforward. First of all, notice that you have two important numbers that you need to represent on your number line here, negative 2 and positive 3. And the first one here says x is less than or equal to negative 2. Less than means to the left. And then it is or equal to, so we have a bracket there. And then I'm going to graph the other set of numbers, x is greater than 3, on the same number line. So if it's greater than 3, we are going to the right of 3 in this direction. But it's not equal to, so we're going to have a parentheses here. Now in the first set of numbers, we are coming from negative infinity. And in the second set of numbers, we are going to positive infinity. And so in interval notation, we are coming from negative infinity up to negative 2, including, and then we're starting at 3 and then going to positive infinity. And we're putting these sets together, or means we're combining these sets. And so what we're doing is we're taking what's called the union of these sets. And the symbol for union is this symbol here. So it kind of looks like a U without a tail. And one other thing that I need to mention that I haven't mentioned so far is anytime you have an infinity or a negative infinity in your interval notation, you never include those numbers, right? Because actually they're not numbers, they're concepts. Okay, so negative infinity and positive infinity should always have a parentheses next to them. In our next example, we want to graph the set of numbers x such that x is greater than negative 1 and x is less than 2. So for this, I'm going to take a slightly different approach because I have the word and in there. So first of all, here's -1 on the number line, and here is +2 on the number line. I'm going to sketch a graph of x is greater than -1 above the number line. So you can all see that -1 starts here. So if I go above the number line, that set of numbers can be represented by that graph, right? And it's a parentheses because it's not included. But then we also need for x to be less than 2. So here's 2 over here, and we want it to be less than 2. That's this way. Now the word and means we need both of these to be true at the same time. Okay, so the word and means both must be true. So when you compare that to the word or means you simply take everything that you graph. Here we are not going to take everything that we graph. We're only going to take the numbers that satisfy both of these. And that would be all the numbers in between -1, not including, and +2, not including. And so in interval notation, that would look like this. Now, you can also express this in inequality notation. We are simply taking all the numbers x that are less than 2, but also bigger than -1. And this notation here is called a continued inequality. Now, again, I want the answer in interval notation, but we should understand both of these just for clarity. So here we want to solve and graph the following continued inequality. Notice that what we have here is -3 less than or equal to 2x minus 5 less than or equal to +3. So first, to get the x by itself in the middle, I'm going to add 5 here. But if I do that, I need to add 5 to all 3 parts of this continued inequality. Doing this, we get +2 less than or equal to 2x less than or equal to 8. Next, to get x by itself, we need to get rid of the 2 here. So I'm going to divide by 2. And when you divide by +2, you get those numbers, and the inequality symbols do not change. And so this is our solution. Now we need to graph that solution. So on a number line, we are looking at all of the numbers x that are in between +1 and +4, including the endpoints. And so in interval notation, this would be 1 to 4 with brackets. Next, let's go ahead and solve the compound inequality. So now I have 2 inequalities separated by the word or. So in this case, all you need to do is solve each one of these separately. So here's the first inequality. We can solve this by subtracting 7 from both sides, and then dividing by 3 on both sides. And this gives us t must be less than or equal to -11/3. And now for the second inequality, 3t plus 7 is greater than or equal to 4. Again, I'm going to subtract 7 from both sides, and then divide by 3. And this gives us t is greater than or equal to -1. And now we're going to graph the solution and put it in interval notation. So on a number line, -11/3 is to the left of -1. And we want all the numbers that are less than or equal to -11/3 or greater than or equal to -1. And so again, remember, you have infinity and negative infinity. And so in interval notation, we're going to use the union symbol. And this is our final answer. Now we're going to move into quadratic inequalities. So notice that now you have an x squared involved. When you have a quadratic inequality, the process is completely different. So first thing you want to do if you have an inequality that is not linear is you want to get 0 on one side of the inequality. Okay, so we already have that, so that's good. Then we're going to factor the left-hand side. And the factorization here is pretty simple. If you want, you can pause and make sure that you understand this factorization. And then what I'm going to do next is I'm going to solve the equal to 0 part. So we know that this will equal 0 when x minus 4 equals 0, which means x would be 4. And we know it's going to also equal 0 when x plus 2 equals 0, and that means x equals negative 2. Now here's where it's different. If you look at this on a number line, we have the solutions positive 4 and negative 2. But this is only where it's equal to 0. We also want to know where is it less than 0. And there's a couple of different ways to do this. Basically, this number line gets divided up into 3 parts. We have all the numbers that are less than negative 2, all the numbers in between negative 2 and positive 4, and finally all the numbers to the right of positive 4. Some of these numbers will satisfy this and some of these numbers will not. So one way to do it is to simply test each interval. So I can pick a number that is less than negative 2, for example, negative 5. I can pick a number that is in between negative 2 and positive 4, maybe 0. And finally, I can pick a number that is greater than 4, like maybe 10 or something like that. And now I'm just going to plug those numbers into my factored inequality. So for example, when x is negative 5, we get negative 5 minus 4 times negative 5 plus 2, which is equal to negative 9 times negative 3, which is equal to 27. And now I just need to ask, is that less than or equal to 0? The answer here is clearly no, right? Because 27 is positive, so it is not less than 0. So the number negative 5 does not work. And that means that no number in this interval is going to be a solution. Then we do the same with the next test number, which is x equals 0. If I plug in 0, we get 0 minus 4 times 0 plus 2, which is negative 4 times positive 2, which is negative 8, And we ask, is this less than or equal to 0? And the answer here is yes. Negative 8 is less than or equal to 0, which means this number works, which means all the numbers in between these two numbers will work. And finally, we test our last interval by using the number 10. If I plug in 10, we get 10 minus 4 times 10 plus 2, which is 6 times 12. And 6 times 12 is 72. And again, is this less than or equal to 0? No, it is not. So 10 does not work, which means the whole interval fails. So our solution is all the numbers that make the original true. And that's going to be all the numbers from negative 2 to positive 4. And don't forget, this is inclusive because we do have an equal sign there. Let's go ahead and take a look at the next problem here. We have x squared minus 6x plus 9 is greater than or equal to 0. So first of all, I want to make sure I have a 0 over here. So this is good. Check that off the list. Next, I'm going to factor the left-hand side. Now, the left-hand side factors into x minus 3 times x minus 3, which is actually x minus 3 quantity squared. Now I'm going to say, well, when is this equal to 0? Well, if I set x minus 3 equal to 0, we get x equals 3. We get a single number. Now we're going to draw a number line, just like we did in the previous problem, and we are going to test to the left of 3 and to the right of 3. So the test numbers that I choose are x equals 0 and x equals 4. Okay? Plug those in. So if I plug in x equals 0, and I'm going to plug it in right here, that gives us 0 minus 3 times 0 minus 3, which is negative 3 times negative 3, which is positive 9. Is this greater than or equal to 0? And the answer is yes. So these numbers here all work. What about x equals 4? Well, if I plug in 4, I get 4 minus 3 times 4 minus 3, which is 1 times 1, which of course is 1. Is that greater than or equal to 0? Yes, it is. So this number also works. So all these numbers work. Now, the only other question we have to ask is, what about 3 itself? Does 3 work? The answer here is yes, because we have inclusion on our inequality, right? It's greater than or equal to. And of course, if I plug in 3, we get 0. So all the numbers to the left of 3 are included in the solution. All the numbers to the right of 3 are included. And 3 itself is included. So the solution here is all real numbers. And all real numbers in interval notation is all the numbers from negative infinity to positive infinity. Our next example is a rational inequality. So we have x minus 4 divided by x plus 1 is less than or equal to 0. Once again, the first thing you want to do is make sure you have 0 on the right-hand side there. And then it's just like the quadratic inequalities. What I'm going to do is set each of these factors equal to 0. And that's going to give us x equals 4 and x equals negative 1. Now, put aside the fact that you know you can't plug negative 1 in here because negative 1 plus 1 would be 0. But for the purposes of finding the intervals, we still need to consider negative 1. So on a number line, we're going to test all the numbers in these 3 intervals. Here are my test numbers that I would like to use. You do not have to use these exact test numbers. You can just pick any number that lies in these intervals. And then I'm going to plug those in. And I'll do the work off camera. All right, so here I have tested each of these intervals by using the test number. And what you can see here is the only interval that works is the interval that contains x equals 0, and that is this interval right here. Now, our solution, you can see the inclusion here, so you want to include. So we are going to include 4, of course, but we cannot include negative 1, because if you plug negative 1 in here, you will be dividing by 0, and we cannot divide by 0 ever. So our final solution here is all the numbers in between negative 1 and 4, including 4, but not including negative 1. And for our final example, it's another rational inequality. Notice once again, you have 0 on the right-hand side, so this is good. But the first thing we need to do here is we need to combine these fractions together. So we need to get a common denominator and add those fractions together. So we have 3 over x minus 2 minus 2 over x minus 3 is greater than 0. So what I'm going to do is multiply the top and the bottom of this fraction by x minus 3 and the top and bottom of the second fraction by x minus 2. And this will give us a least common denominator of x minus 3 times x minus 2. Next, I'm going to multiply out the numerator here. That's 3x minus 9 over x minus 2 times x minus 3. Now, for the second one here, you got to be a little bit careful. You have a minus sign here. I'm going to distribute only the 2 at first. So I have 2x minus 4 on top. Denominator, of course, is the common denominator. And then in our next step, we need to make sure that we distribute this negative sign as well. So when we combine these into a single fraction, we have our common denominator. And then on top, we have 3x minus 9 minus 2x, and then minus 4 is positive 4. So again, you are distributing that negative there. And we want to know, when is this greater than 0? So combine like terms on top. We have x minus 5 divided by x minus 2 times x minus 3 greater than 0. And now we're going to have 3 numbers that make each of these factors equal to 0. And those numbers, of course, are going to be 5, 2, and 3. So let's put those on a number line. Make sure you put them in the correct order. So 2 goes first, then 3, then 5. And now we're going to test our intervals. Now, I'm going to not pick test points on this. I'll leave this to you, but pick a test number for each of these intervals and then plug it in. The only one that's a little bit tricky is, for this interval here, you're going to have to pick something like 2.5, right? You have to pick a number between 2 and 3. But for all the other ones, you can pick whatever you want. I guess I will pick numbers. All right. Plug those in and see which numbers work and which numbers do not work. Okay, once you've done that, what you should find is the numbers that work are the numbers in between 2 and 3, and the numbers that go from 5 to infinity. Now, we are not including anything here, so the interval notation is going to be all the numbers from 2 to 3, union all the numbers from 5 to infinity. Let's clean this up a little bit. There we go. And that concludes this video lesson.